Section 11.5 Polar Coordinates. Our objectives are to locate points in the polar coordinate system, to convert between coordinates in the rectangular and polar systems, and to create graph of equations in polar coordinates. In two-space, we normally assign a fixed point with a coordinate pair x and y. But that's not the only way we can specify a point. We can also use a radius and an angle. Now, for these points that you have in a rectangular coordinate system, so we would normally go over x units and then up a y value units. So let's say that this right here, this distance is your x, and this distance from here to here is your y, and that gives you the point x comma y. Now when we're working in the polar coordinate system, with polar coordinates, we're going to give, instead of this distance x and y, then now instead we're going to represent this distance by the angle measurement theta and this distance r. So the first thing we need to talk about is that the origin, instead of being called the origin, is called the pole, and the x-axis that extends this way to the right is called your polar axis. So that's the x-axis. This distance from here to here is your distance of r, and this would be the distance of theta. So that gives you your r comma theta. Both r and theta can be either positive or negative. So depending on this, depends on which way we're going to move on our graph. Remember, when theta is positive, we go in this direction this way. And when theta is negative, we go in the counterclockwise direction. So this would be a negative angle. The other way was positive. So that's what this statement right here says. When r is positive, the polar distance is measured from O along the terminal side of the angle theta. When r is negative, it's measured from the opposite side of the terminal side of theta. So kind of with when we did vectors, remember we said when we had a negative vector, it went the opposite direction. That's the same idea when we're doing our polar graphing. So let's go ahead and take a look at these values that we have right here. The polar coordinates of a point P, the main thing to remember for this is that they are not unique. By not being unique, that means that there are many representations for a polar coordinate, not just one. Like in the xy coordinate plane, x and y is always going to be just x and y. But in a polar graph, it's not just that point, because remember, we said that we have coterminal angles for the coordinates. So I know that if I have this r value of 2 and I have pi over 3, I know that's not the only way that I can represent that point. Remember, if we go all the way around once, so if I take pi over 3 and add 2 pi to this, so if I add 2 pi, I need a common denominator, which would be 3, so that would become 6 pi over 3. I get 7 pi over 3. And remember, that's a coterminal angle. I just went all the way around my circle once and ended up at the same spot, which is right here. So that would be another representation of the same points, but with a different angle. I can also go in the negative direction. So if I go negative direction this way, negative pi over 3 is also coterminal with pi over 3. So this point can also be represented by 2 negative pi over 3. Now, those aren't even the only 3 different ways. There are infinite many different ways that I can represent these points, because I can keep on going around and finding coterminal angles with these. I can also use r as a negative value and do the opposite. So if you look here, we have pi over 4, which is this distance here. So this point can be represented by 2 pi over 4. If I have negative 2 pi over 4, then the direction would be this way, and I would land on this point here. So negative 2 pi over 4 would be there. I also know that if instead I did negative 2 and then did the negative of this angle, I could also come up with that point. So we're going to do that in a little bit. I'll just hold off to that for right now. For this next one, we have this distance from here to here, we're saying is 7 pi over 6. So for this 7 pi over 6, I know that 3, 7 pi over 6 is this point right here. If I do negative 3, 7 pi over 6, I know that I have 7 pi over 6 down here. That means I'm going negative 3 in this direction backwards. So that would represent this point here. So you just have to remember the negative means for the R value means you're going the opposite way. So then if I have pi over 2, negative 2.5, so pi over 2 negative would be down here. So this would be 2.5 negative pi over 2, but if I have negative for my R value, I end up over here. So you have to remember that it's the opposite. So let's go back to our graph over here and let's graph and plot some of these points. So for example, let's graph all of these. Now, when you're graphing in the polar system, notice that it's circular, and also notice that we can use degrees or we can use radian. So it doesn't really matter which one you use. Usually, if you look at the points, if you see a degree symbol, you're going to use degrees. If you see radians without the degree symbol, you're going to use radian measures. How do I know what each of these values are going by right here? Well, the way that you can do that is you can count how many you have. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 between 0 and 90. So if I do 90 divided by 9, I get 10. So I know that each of these are going by 10 degrees. So that would be 10, 20, 30, 40, 50, 60, 70, 80, 90, and I can keep on going around my circle. So that's just to show you how to get each of the lines that you have. Now, for this, the first point that we want to graph is for 60 degrees. You can graph it if you want with finding the radius first and then the angle. I happen to find it's a lot easier to do the theta first and then graph what R is. So in this case, I know theta is 60 degrees. I have an R distance of 1, 2, 3, 4. So I'm taking this and I'm moving it to 60 degrees, which would be right here. So the way that we do this point is we would just put a dot right there. So I don't actually draw the line, but I know the distance from here to here is my R value, which is a distance of, again, 4. So that would be for point A in the polar system. So this is A. Now for B, I have 6, 270. So I want to find 270, which would be down here. And so I have 6, so 1, 2, 3, 4, 5, 6 would be right here. So the distance from here to here is a distance of 6, and I went all the way around to there, which is 270 degrees. So again, I don't need all of that, I just need the point right here, which is B. For the next one, let's go ahead and do C. We have -5 and 30 degrees. So here's 1, 2, 3, 4, 5, and 30. But the problem is I have -5, 30. So that means I need to go in the opposite direction. 1, 2, 3, 4, 5. So this would be -5, 30 right there. Just remember, the negative means you go opposite like the vectors. So this is going to be point C. Let's go ahead and do D. D is 150 and -3, 150, so 150 degrees I know is going to be all the way to here. And if I did +3, 150, I'd be right there, but we want the negative direction, so that means I'm going to go the opposite way. And that would be my answer, so this is going to be for C. And then now this one on your paper is E and F. I just forgot to change it up here. So we have -7, 120 degrees. So 120 would be from here to here. -7 means I'm going the opposite direction. So 1, 2, 3, 4, 5, 6, 7 would be right there. So that's E. And then the next one we have is F. Now notice F is different from the rest because it doesn't have a degree symbol for theta. We have pi over 4. So recall that pi over 4 is really 45 degrees. So I have 3, 45 degrees is what I'm really looking at here. So 45 degrees is in between 50 and 40 degrees. So right there. So we have 3 and pi over 4, so I'm going to measure a distance of 3 for that line. which would be right there. Now, as we said before, remember we said that these points are not unique. Since these points are not unique, that means that there are infinite many ways that I can represent each of these points that we have. So if, for instance, if we look at the point A, I have 4 60 degrees. Well, let's come up with some other ways that we can represent this point. So let's go ahead and maybe go do a coterminal angle with 60. So if I go all the way around and back, that would be, I'm adding 360 to 60 degrees. So 360 plus 60 gives me 420. So 4, 420 degrees is the same point as 460. Now I could keep going around if I want, or I could also do the negative direction. So if I go in the negative direction starting from here to here, well, I know that I'm taking 360 minus 60 then, so that would be negative 300 degrees if I started at the 0 and all the way to here. So, and then this line is what I'm looking at. So that would be 4, negative 300 degrees. That's still not the only way that I can represent this point. Another way that I could represent this point would be, of course, to do the negative. So instead, if I did 1, 2, 3, 4 would be right here. So if I was here and then did the negative of my answer for this angle measure, that would also work. So from here to here would be 240. So if I did 4, negative 4, 240 degrees, don't forget my degree symbol. Oops. Sorry about that. So if I did negative 4, 240 degrees, that would be all the way around to here, but then negative means I'm going the opposite direction, so I'd be back at A. And if I did instead maybe, let's go from here to here, which would be negative 1, 2, 3, 4. So if I went from here to here, I know that, so now I'm going to go negative direction for a negative angle from there to there. So I know that in the negative direction, if I do this from here to here, I get negative 130, because you're just going to subtract 240 minus 360, which gives you this value. So notice that if I did the negative angle, well, how would I get back to angle A? I would have to, sorry, I accidentally put 130, but meant negative 120. So I went negative 120 in this direction. Well, then I need to go in the opposite direction in order to get to A. So if I did a negative R value, so negative 4 and negative 120 degrees, I would be back at A. So I could keep on going and find more and more representations for point A, and I can do this for all the different points that I have. And then also just to look down here, so again, remember this is the pole, this is the polar axis, and notice that each of these points are now represented in polar coordinates, which is okay to do. So we already did this example right here. So we wrote it, it says name 2 other pairs of polar coordinates that could describe point A. So we have already done that. Now we want to convert between rectangular and polar coordinates. Since a point in space can be specified using either x and y or r theta, it's logical to conclude that there must be equations to convert from one set of coordinates to another. Now if we think about having x and y, then I can solve for theta by using tangent. So if I know my x and y coordinates, I know that the tangent of theta is equal to y over x, opposite over adjacent. So into theta would be equal to the tangent inverse And if I have r, or if I want to solve for r, I know that I can make this a right triangle and use the Pythagorean theorem. So r squared is equal to x squared plus y squared. So r is equal to the square root of x squared plus y squared. Now, let's say that instead of being given x and y, I was given my distance of r to this point and theta, and I want to find x and y. So if I want to do this and find x and y, well then I know this is x and this is y. I can use right triangle trigonometry. So to find x, I can do the cosine of theta equals x over r. So x is equal to r times the cosine of theta. And y would then be equal to the sine of theta equals y over r. So r times the sine of theta gives us our y. So again, just using things that we've done before, so it's nothing new. Now we're going to convert each point from polar coordinates to rectangular coordinates. So if you don't see a degree symbol, you're using radians. Now looking at these points that I have 2 pi over 4. So again, remember your x is equal to r times the cosine of theta. Y is equal to r times the sine of theta. So for this first one, x is equal to 2 times the cosine of pi over 4. Since pi over 4 is on my unit circle, I can use that because I know it's root 2 over 2. So 2 times root 2 over 2 is equal to root 2. Y would be equal to 2 times the sine of pi over 4, which again is 2 times root 2 over 2, because it's really over 1, so that I get root 2 divided by 2 cancels out, so I get root 2 again. So that means my rectangular coordinates are root 2 comma root 2. So I just made it a little bit smaller, so that's my solution right there. And I can kind of confirm to see if this makes sense. If I have an r value of 2 and pi over 4, well, I know that 1, 2, so that we said this was 2, pi over 4 is 45 degrees, so it would be right there. And that makes sense that this would then be root 2, and this would be root 2 for my, my rectangular coordinates. So let's go ahead and look at the next one. Same thing. To find x is equal to r times the cosine of 2. Y is equal to 3 times the sine of 2. Remember, again, this is in radians, so make sure your calculator is in radians to figure this problem out. And since it's not in my unit circle, I'm going to just plug it into my calculator, and I get negative 1.25, comma 2.73. And then if you think about this on your graph, well, remember that this is pi over 2, which is about 1.57. Notice that 2 is the radian measure we're using. 2 is bigger than 1.7, and this is here pi, which is 3.14. So I know it's going to be somewhere in between here. So I have 1, 2, 3, and the angle measure here to here would be 2. So does it make sense that I have negative 1.25, which is here, and up 2.73? That, yes, that makes sense because of where I'm at on my polar graph to rectangular. And then we can do the same thing with the last one. So x is equal to 8 times the cosine of 30 degrees. Y equals 8 times the sine of 30 degrees. Notice that you have degrees here. So make sure your calculator would then be in degrees, or we know that 30 degrees is on my unit circle, so that I can use that. So for the first one, 30 degrees is really equal to root 3 over 2. So I'm just going to write that next to here. So I have 8 times root 3 over 2, and this would be 8 times the sine of 30 is 1/2. So I end up with 8 divided by 2 is 4, root 3, comma 4. Now we're going to convert each point from rectangular coordinates to polar coordinates. To do this, recall that there are an infinite many solutions. when you're going from rectangular to polar. And the reason that is because we can have many different representations like we showed earlier with the point A. So for this, I'm going to find 2 of them for the first one, and then we'll just finish the rest. So for the first thing, I know to find theta, it's equal to the tangent inverse of y over x, and I know that r is equal to the square root of x squared plus y squared. We found those formulas a minute ago. So in this case, theta is equal to the tangent inverse of root 3 over 1. I know that that's on my unit circle. So if you think about your unit circle, I know that this is in quadrant 1. And so root 3 over 1 I know is equal to pi over 3. I can also have other angles that are equal to pi over 3, such as if I add 2 pi to this, I get 7 pi over 3. If I do the negative angle of pi over 3, I get negative pi over 3, so that's why there's many representations. R would then be equal to the square root of 1 squared plus root 3 squared. So r is equal to the square root of 1 plus 3, which is equal to 2, because the square root of 4 is 2. So that means that one possibility I could have is 2 comma pi over 3. If I do a coterminal angle, I could do 2 comma 7 pi over 3. Or I could also do the negative angle, 2 comma negative 5 pi over 3. So those are all the same thing. And there's many other possibilities. So these are just a few of the answers. Kind of to check my answer, I have over 1 up root 3. So something like this. So again, for the first one, we just did, let me make that larger. So for the first one, we just did pi over 3 and then the point. And then for the next one, we went all the way around to get 7 pi over 3. And for the last one, we did the negative of the point. We could also do one with a negative r value if we wanted to as well. I'm going to skip that for right now, though, and move along. So then, looking at B, we're going to do the same thing. I know that theta is equal to the tangent inverse of negative 3 over 3, which is negative 1. Negative 1's on my unit circle, so the tangent of negative 1 would be equal to negative pi over 4. Or remember, we can also use 7 pi over 4 on my unit circle. R is equal to the square root of 3 squared plus negative 3 squared, which is 9 plus 9, which is root 18, which simplifies into 3 root 2. So then one ordered pair that I could have in polar would be the points 3 root 2 comma negative pi over 4. Or I could do 3 root 2 comma 7 pi over 4. And of course there are many other answers that I can have. So for the next one, let's do the same thing. Theta equals the tangent of inverse of 2 over 0. Remember, we can't divide by 0, so now I'm looking for sine over cosine where this cosine is 0. Cosine is 0 if you think about your unit circle here and here, so I have to figure out which one I'm using. Well, if the point 0, 2 is right here, so I know I cannot use 3 pi over 2, I'm going to be using pi over 2. And then r is equal to the square root of 0 squared plus 2 squared, and 2 squared is 4, so that gives me 2. So then one possible answer that I can have would be 2 comma pi over 2. Let's do a negative r value for this one. So if I went all the way around to 3 pi over 2 and was here, I would have to use a negative r value to get to here. So if I did negative 2 comma 3 pi over 2, that would work. So then for the very last one, same thing. Theta is equal to the tangent inverse of negative 4 over negative 1. That's not on my unit circle, so use your calculator to get theta is equal to 1.34. And then r is equal to the square root of negative 1 squared plus negative 4 squared. So 1 squared is 1, 4 squared is 16, so that gives me root 17. So then my polar ordered pair, one of them could be 1.34 comma root 17. And again, there are many other possible answers for these. Now, the last part we want to talk about is polar graphs. Polar graph is a graph of the set of all points r theta satisfying the given polar equation. The two most basic polar graphs are r equals c, which is the circle of a radius c, and r equals theta, which is a line through the origin that forms an angle of theta with a polar axis. Now, if you look at the first one, we have r is equal to a value of 3. So that means when the radius is 3, it doesn't specify what the angle is. That means I can have any angle with a radius of 3. So if you look, that means this is what you would have right here. And we would be going in this direction to make the circle because r is positive. So it would go clockwise. For the next one, we have r is equal to negative 2. So if r is equal to negative 2, then instead of starting at positive 2, we would be starting back here, and we would be going around our circle. So then that would be a radius of 2. So then for the next one, we have theta equals 30 degrees. So when theta is equal to 30, that means we can have any r value that we want. So I just have to find 30 degrees on my graph. So 30 degrees would be right here. So if this is 30 degrees, then I know my line would go like this. And I can find out what each of these are going by. I know it's going by 15 degrees for each of them. And the reason I know it's going by 15 is because there's 6 lines between 0 and 90. So 90 degrees divided, or 90 divided by 6, it gives us 15 degrees, which tells me that that's what each of these lines are going by. So then for the next one, I have theta equals negative 45 degrees. So on here, negative 45 degrees would be down going this way in the negative direction. So we want any r value with theta being equal to negative 45, so that would be this line right here. So what we're going to do next is we're going to actually be practicing polar graphing on our graphing calculator, and we're going to be graphing